Okay, so the first lesson, or the most first important point of Chapter 6, is that enzymes work by reducing the free energy of some reaction transition state. Okay, and this is accomplished by creating specific three-dimensional interactions. So these are specific interactions just like that stabilize the complex between the protein and the substrate, and that these are arranged in three-dimensionally in space to stabilize the geometry of the transition state. So these interactions are the same types of interactions that we learned about that stabilize protein three-dimensional structure: hydrogen bonds, hydrophilic, polar interactions, hydrophobic interactions, etc. So these same things are involved into interactions between the protein in the active site or the binding site and the groups on the substrate. Okay, now let me draw some free energy plots here to be a little bit more specific. So here is a graph of free energy, and here we have a reaction coordinate. Okay, so here's my reaction. Let me draw this baby. There we go. So you will see that we have a reactant on this side. The reactant is over here, and then we have a product here. The transition state is this up here. This represents the transition state up here, that peak. So let's just remind ourselves what some of these values are. This difference here, right, is the difference in free energy between the reactant and the product. This distance here, right, and that's delta G0. Delta G0 is the standard free energy change for that reaction. But you'll also see that there's a energy difference between the top of the transition state there and the initial energy of the reactant. That right there is called the free energy of activation, okay? The activation energy. Okay. If this is for the uncatalyzed reaction, the presence of the catalyst will lower the energy of the transition state. Okay, so here's the transition state. It's going to lower that. So let's draw another dashed diagram like this. So you can see that the catalyzed reaction, which is represented by this dashed line, has a smaller energy of activation. That smaller energy of activation will lead to a greater rate of forward reaction as well as backwards reaction. In fact, they're both increase the forward and the reverse. So this leads to one important point, which is that the presence of a enzyme, it doesn't change the equilibrium constant. So the equilibrium constant here is unchanged. And that's both the forward and the reverse reactions are increased. The rates are increased here. All right, now I want to draw a free energy plot looking a little bit more in detail at these at the enzyme catalyzed reaction. Okay. So here is my free energy, and now what I'm going to do is I'm going to put in various intermediate steps here. Particularly, I'm going to put in the enzyme substrate complex. Again, here's my reaction coordinate, and this represents the product. This represents the transition state. This represents something that I'm going to call ES, where E stands for enzyme, S for substrate, and this is E plus S. In other words, the enzyme and the S in free solution floating around there, but they haven't encountered each other. ES represents the binding of the substrate. Again, this is a non-covalent complex. Okay, on this diagram, the transition state energy, or the activation energy, is going to be represented by this distance here. So that's our delta G, double dagger there. That's the activation energy. Okay. Now you'll notice that there's something different about the transition state. The transition state is at the peak. Okay, so a transition state is really not a well-defined thermodynamic state. That means that that state is not occupied, or the system doesn't exist in that state for any measurable amount of time. It's fleeting. It passes through it very rapidly. The dissociated complex, the enzyme substrate complex here, they both can exist for a certain amount of time and can actually interconvert. But this state right here is fleeting. When the system moves to this state, it rapidly either falls down to either side. And the product is a well-defined state. So that's something important to think about, that the transition state itself is not really a thermodynamic state in the same sense as the others, and it's difficult to observe experimentally. Okay, another thing you notice about this diagram is that the energy barrier, this is an energy barrier between the dissociated enzyme and substrate and the complex. That energy barrier is actually much less than the activation energy, which implies that the interconversion between these two states is much faster than this, and that's often the case. So this is sort of an energetic description of the association and dissociation of this complex. So the substrate can bind to the enzyme, and more often than react, it can actually come off back in the solution unreacted. This hints that you can have sort of an equilibrium existing between the dissociated and the associated state here before, that's much faster, that's reached much faster than this slower conversion to product. And that's going to be an assumption that will help us in simplifying or interpreting the Michaelis-Menten model, which we're going to deal with next.